Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to close your eyes for a second. Well, don't close them if you're driving, obviously, but picture the absolute worst place you can possibly imagine.
Okay.
And I don't mean the DMV on a Friday afternoon, and I don't mean, a crowded subway car where the AC has broken. I mean a place where the environment itself is actively trying to kill you in about 4 different ways simultaneously.
You are painting a lovely picture.
I try my best, but seriously, imagine a world where the air pressure is so heavy it would crush a nuclear submarine like an empty soda can.
Mm-hmm.
The temperature is hot enough to melt lead. Literally, a pool of lead would be a liquid puddle on the ground.
475 degrees Celsius, just searing.
And to top it off, the clouds aren't made of water vapor. They're made of concentrated sulfuric acid.
You are describing, of course, Earth's so-called evil twin.
Venus, the planet that has been the graveyard of so many robotic explorers.
It is a fortress. That is the best way to describe it. Historically, when we send landers there, like the Soviet Venera probes back in the day, they survive for maybe an hour, maybe 2, before the electronics fry or the hull buckles.
Just get cooked and crushed.
Instantly. It is a world that keeps its secrets very, very well hidden under those thick, toxic clouds.
Exactly. It's the ultimate look but don't touch scenario. But today, Monday, February 9th, 2026, we are not just looking at the fortress walls. We are cracking them open. Because there's breaking news today that fundamentally shifts our understanding of this hellscape.
It really does. This is one of those days when the textbooks get a little update.
Researchers from the University of Trento have confirmed the first direct physical evidence of a subsurface lava tube, essentially a massive cave on Venus.
And we need to be clear about the magnitude of this. We aren't talking about a suspicion. We aren't talking about a mathematical model that suggests maybe there are caves.
This isn't a we think.
No. We are talking about hard evidence, a direct observation.
This is the difference between guessing your neighbor has a basement and actually seeing the stairs leading down into the dark.
Precisely. And finding this on Venus, of all places.
Yeah.
The stakes are huge. We have seen lava tubes on Mars. We have seen them on the moon. They are fascinating there.
Right.
But finding one on Venus, hidden beneath that opaque atmosphere, validates decades of geological theory.
So we are basing this entire deep dive on the primary source material, a brand new paper published today in Nature Communications titled Radar-Based Observation of a Lava Tube on Venus. It's led by Lorenzo Bruzone and his team at the University of Trento.
A fantastic piece of research. It is incredibly detailed.
And our mission for this deep dive is to really unpack this discovery. We aren't just talking about a hole in the ground.
No.
We need to talk about the detective story, how they found this using data that is technically older than I am. We need to talk about the sheer scale of this thing, because when I read the numbers, my jaw hit the floor. This isn't a crawl space. It's a tunnel large enough to fit a city block.
It puts our terrestrial caves to shame. Utterly.
And finally, we're going to discuss what this tells us about the volcanic history of our planetary neighbor. So buckle up. We are going beneath the clouds.
Into the dark.
Let's start with the detective story. Because usually, when we get breaking space news in 2026, it's from a flashy new robot, right?
Mm-hmm.
We're used to the James Webb Space Telescope beaming back high-res images of galaxies, or a rover on Mars drilling a new hole.
Correct. We are accustomed to fresh data, new photons hitting a new sensor.
But that is not what happened here. This discovery is a bit of a ghost story.
It is. To understand why, you have to understand the fundamental problem with exploring Venus. If you orbit Mars, you can bring a nice optical camera, basically a really expensive DSLR, and take a photograph of the surface.
And you see the ground?
You can see the red rocks, the dust devils, the crater rims. It's intuitive. We understand pictures.
But if you orbit Venus and take a photo...
You see a cue ball.
Right.
You see a bright, featureless white sphere. Maybe a few swirls in the upper atmosphere, but that's it.
Because of the clouds?
The atmosphere is incredibly thick and opaque. Visible light just bounces off the top of the cloud deck. You cannot see the ground. So if you want to map the surface of Venus, you cannot use a camera. You have to use radar.
You have to scream at the planet and listen to the echo.
That is a very aggressive way to put it. But yes, essentially, you bounce radio waves off the surface and measure how they come back to you. The timing, the strength that builds a picture.
And that brings us to the time capsule aspect of today's news. The data that the University of Trento team used, it didn't come from a ship currently orbiting Venus.
Not at all.
No. It came from NASA's Magellan spacecraft.
Which is a name that should trigger some nostalgia for some of our listeners.
Seriously. Magellan launched in 1989. It was deployed from the space shuttle Atlantis. I mean, we're talking about a different era of space exploration.
Pre-internet, practically. It mapped Venus between 1990 and 1992.
Okay, 1990 to 1992.
And then it was intentionally steered into the atmosphere and burned up in 1994.
So let's pause and appreciate this. The spacecraft has been vaporized for over 30 years. It's gone.
Completely gone.
But we are still making headline discoveries in 2026 from the data it sent back when the internet was barely a concept.
It is a testament to the quality of that mission. Magellan was a workhorse. It mapped about 98% of the Venusian surface with its radar. But it also highlights a very important concept in modern science: data archaeology.
Data archaeology. I love that term. It makes me picture Indiana Jones, but instead of a whip, he has a hard drive.
Ideally with fewer booby traps. But the concept is sound. The pixels, so to speak, the raw radar returns were always there. They were sitting in NASA's Planetary Data System archives.
Just waiting.
Just waiting. But in 1992, we didn't have the processing power we had today. We didn't have the sophisticated algorithms to filter out noise and enhance the signal. It was cutting edge for its time, but by our standards.
It's like trying to play a modern video game on a computer from 1992. You just can't.
Exactly. The hardware and software couldn't do what we can do now.
So the picture didn't change, but our glasses got better.
That's a perfect analogy. The data is a fixed asset. It doesn't rot. But our ability to understand it evolves. Lorenzo Bruzone and his team at the Remote Sensing Laboratory, that's at the University of Trento, they didn't just casually scroll through the old images.
No, this wasn't an accident.
No. They developed a specific new imaging technique. They created new tools to look at this old information.
They were looking for something specific, right? They weren't just browsing.
No, this was a targeted hunt. Their goal, as stated in the paper, was to detect and characterize underground conduits.
Conduits. A fancy geological word for tunnels.
In this context, yes, lava tubes.
Yeah.
They were looking for specific surface anomalies that would hint at a hollow space beneath the rock.
So they are combing through this massive, noisy data set from the early 90s, applying these new algorithms to clean it up to filter out the static.
Exactly. And they focused their attention on a region called Nyx Mons.
Nyx Mons.
A fitting name for a dark discovery.
Why is that? What does it mean?
Nyx is the Greek goddess of the night.
Spooky. I like it. So, a mountain of night.
Nyx Mons is a large volcanic rise in the northern hemisphere of Venus. It's a place that has fascinated geologists for a while because it shows signs of heavy volcanic activity. Lots of lava flows, lots of fractures. It's a geologically interesting place.
So if you're going to find a giant lava tube, a big volcano is a good place to start looking.
The best place.
Okay, so they are looking at Nyx Mons, but here is the part that confuses people, and it confused me at first. You said Magellan used radar to map the surface?
That's right.
Radar bounces off the ground. It doesn't go through the ground.
That is correct. At least Magellan's specific radar frequency could not penetrate deep into the rock. It just tells you what the surface looks like, its roughness, its slope.
So if there is a tunnel underground and the roof is solid rock, Magellan would just see a flat plane. It wouldn't see the tunnel.
Exactly. You would fly right over it and never know it was there.
So how did they find it? What was the clue?
They had to look for the smoking gun. In planetary geology, when you are hunting for lava tubes, you are actually hunting for skylights.
A skylight. Okay, let's unpack that. When I hear skylight, I think of a nice window in a kitchen to let some sun in.
Not quite, though the principle of letting light in is similar, or in this case, letting radar in.
Got it.
Think about how a lava tube forms. You have a river of lava. The top cools and hardens into a roof because it's exposed to the air. The lava inside keeps flowing and drains away, leaving a long, hollow tunnel.
Like a subway tunnel, but made of basalt.
Right. Now imagine 1 million years pass. Maybe a meteor hits the area. Maybe a Venus quake shakes the ground. Or maybe gravity just wins, and a section of that roof becomes unstable.
It caves in.
It caves in. And that collapse creates a pit on the surface. A hole. That pit is the skylight. It connects the surface world to the underworld.
So if you spot the hole, you can infer the room below it.
It's the one.
You can't see the tunnel directly with Magellan's radar, but you can see where the roof failed.
That is the logic. And in the Magellan data, Specifically in the Nyx Mons region, they found a series of these features called pit chains. But they focused on one specific feature. It's marked as A in the study figures, that looked exactly like a skylight into a massive void.
But here is the tricky part. I've seen radar images. They are weird. They don't look like normal photos.
They're not intuitive, no.
Bright means rough, dark means smooth.
It's all backwards. How can they tell it's a deep hole and not just a shallow dish or a regular impact crater?
It is all about the shadows. This is where the detective work gets mathematical.
Okay.
In the study, they point out a white arrow in the imagery. That arrow indicates the direction the radar illumination is coming from. Magellan wasn't directly overhead. Its radar beam hit the surface at an angle.
The direction the spacecraft was shining its radio flashlight.
Exactly. Now imagine a deep vertical shaft. If you shine a flashlight across the top of it from the side, the far wall is going to catch the light and be very bright in your radar image.
Okay, it reflects the signal right back. But the near wall, the ring closest to you, is going to cast a shadow down into the hole. And the floor of the pit will be in that shadow. It will look dark.
Ah, okay, I'm visualizing that.
By analyzing how that shadow falls, and specifically measuring the length and intensity of the shadow within the pit, you can calculate geometry. You can figure out that this isn't a bowl shape like a crater. A crater has sloped sides.
Right. The shadow would look different.
It would look very different. The only model that fit the data they were seeing was a deep, steep-walled shaft.
It's amazing what you can do with shadows. It feels very Sherlock Holmes. The shadow is 3 pixels long, Watson, therefore the hole is 400 meters deep.
It is essentially trigonometry and physics.
Yeah.
But yes, it is detective work. They modeled the radar signals against different shapes. A shallow crater, a deep pit, a cone. And the only model that fit the data from Magellan was a deep vertical skylight connecting to a subsurface void.
And that void, well, that's the part that really blew my mind when I was reading the briefing, because we aren't talking about a little crawl space.
No, we're not.
We really need to get into the numbers here. The scale of this thing is hard to wrap your head around.
It is massive. Genuinely geologically massive.
Start with the diameter. How wide is this tube?
The study estimates the diameter is approximately 1 kilometer.
1 kilometer.
Yes, 1,000 meters.
Okay, stop and visualize that seriously. A kilometer is a distinct distance. If you were driving on a highway, a kilometer takes a moment to pass. Imagine a tunnel that wide. You could fit the Burj Khalifa inside it sideways with room to spare.
It is vastly larger than terrestrial lava tubes. It's not even in the same ballpark.
Right. I've been to lava tubes in Hawaii, the Kazumura Cave. It's amazing. It's a fantastic experience, but it's human scale. I mean, some parts are big, like a subway station, but some parts you have to duck.
Exactly. On Earth, a large lava tube might be 10, 20, maybe 30 meters wide.
30 meters would be a big one.
And finding one that is 100 meters wide would be a headline, a major discovery. This Venusian structure is on a completely different scale. It is an order of magnitude larger.
And it's not just the width, it's the protection. How thick is the roof?
Right, the roof thickness. They estimated that there is at least 150 meters of solid rock shielding this void from the surface.
That's a 50-story building worth of rock above your head. Just solid basalt.
And the void itself, the empty space below that roof, is at least 375 meters deep.
So from the floor of the tube to the ceiling is 375 meters.
At a minimum, that's what they can model from the shadows.
It's cavernous. It's practically an underground canyon. It's a cathedral of geology.
And while the direct observation is limited to the area around the skylight, because that's where we can see the shadow, the morphology of the terrain suggests the tube extends for a long way. You can see these chains of pits, these other potential collapses.
So this one skylight is just one window into a whole subway system.
A huge one.
How long do they think it is?
They estimate this specific segment, based on the surrounding geology, is at least 45 kilometers long.
A 45-kilometer tunnel, 1 kilometer wide, buried under a mountain of rock. That is some serious infrastructure.
The researchers use the term pyroduct.
Pyroduct? That sounds like a heavy metal band.
It is the formal scientific term. Pyro meaning fire, duct meaning channel, a channel of fire.
The Pyroducts of Nyx Mons. I'd buy that album.
It does have a certain ring to it, but it describes exactly what this was. It was a massive plumbing system for magma on a scale we just don't have on Earth.
But this brings up the question of why. Why is everything on Venus so extra?
It's a good question.
Why is the atmosphere so thick, the temperature so hot, and now the caves so enormous? Why is this tube so much bigger than what we see on Earth or even Mars?
Because we share a lot of DNA with Venus, planet-wise.
We do. And this is where we get into the fascinating field of comparative planetology. It shows how the unique environment of a planet dictates its geology. It's not just about the rock, it's about the air and the gravity, too.
We know lava tubes aren't unique to Venus, right? We've seen them elsewhere. Correct. As we said, we see them on Earth, usually in places with basaltic lava flows like Hawaii, Iceland, the Canary Islands. We see them on Mars. We've seen skylights on the slopes of the giant Martian volcanoes like Nyx Mons.
And the moon.
And we see them on the moon. They're called sinuous rills. So the recipe is the same. Lava flows, top cools, tube forms.
The mechanism is universal.
The mechanism is universal. But the ingredients, the environmental variables, are different. And the expert analysis in the paper points to two main factors driving this massive scale on Venus.
Okay, hit me with them. What's the first one?
Factor 1, gravity.
Venus is slightly smaller than Earth, right?
Very slightly. Its gravity is about 90% of Earth's. Now, that might not sound like a huge difference to you or me. If you weighed 100 pounds on Earth, you'd weigh 90 on Venus.
Nice instant diet.
Sure. But when you are talking about millions of tons of molten rock flowing across a landscape, that 10% difference in gravity matters. Lower gravity allows lava flows to be somewhat taller and wider because the fluid isn't being pulled down quite as hard. The rock itself can support larger structures if they're collapsing under its own weight.
So the roof can be wider without caving in.
Precisely. We see this effect on the moon, where gravity is very low, 1/6 of Earth's. The tubes there are huge, hundreds of meters wide.
But Venus's gravity is pretty close to Earth's. That 10% can't be the only reason we're going from a 30-meter tube to a 1,000-meter tube.
You are right. Gravity helps, but it's not the main driver. The main driver is likely factor 2, the atmosphere.
The soup.
The soup. The pressure cooker. Venus has an incredibly dense atmosphere, 90 times the pressure of Earth. And it has hot surface temperatures around 475 degrees Celsius.
Now, intuition tells me that if it's hot outside, the lava wouldn't cool as fast. Like, if I pour coffee in a sauna, it stays hot longer than in a freezer.
That is true for the liquid itself. But the paper argues that the dense atmosphere and the specific conditions favor the rapid creation of a thick insulating crust immediately after the lava leaves the vent.
Wait, so the crust forms faster. That feels counterintuitive.
It forms a more robust crust. Think of the lava flow emerging onto the surface. The heavy, dense atmosphere pushes against it from all sides. The interaction between the hot lava and this incredibly dense, hot gas creates a coherent lid very quickly.
Like putting a heavy lid on a pot.
Exactly. And rock is a great insulator. Once that thick crust forms, it acts as a thermal blanket. It traps the heat inside the flow incredibly efficiently.
So it becomes a superthermos. The outside cools just enough to make a shell, and the inside stays molten.
Precisely. A natural geological pipeline. Because that crust forms so effectively and creates such good insulation, the lava inside stays hot and liquid for a very, very long time. This allows it to flow for huge distances, hundreds of kilometers, without freezing up.
And because it keeps flowing for so long and stays so hot,
it creates a process called thermal erosion. The lava is so hot and flows for so long that it actually melts the ground beneath it. It carves its way down into the bedrock.
It digs its own grave, or its own tunnel, I guess.
It deepens and widens the channel over time.
Yeah.
On Earth, lava usually cools and solidifies before it can carve a canyon like that. The flows are shorter. On Venus, the flow just keeps going, eating the rock, expanding the tube, until you get these monster dimensions.
1 kilometer wide.
The study notes that this Venusian tube falls at the upper end of what scientists have predicted, and even observed, on the moon. It creates a scale of volcanism that is distinct to the Venusian environment. It's a product of its unique, extreme world.
It really paints a picture of a planet that was, and maybe still is, violently active. This isn't just a little trickle of lava. This is a planetary artery.
It does. And this discovery validates a lot of theories. You know, Lorenzo Bruzzo mentioned in the press release that for years these theories were just hypotheses. We think there are tubes. The math says there should be tubes.
But scientists hate guessing.
They do. They prefer knowing. And finding physical evidence like this, it's everything. Moving from speculation to observation is the gold standard in science.
It's the difference between suspecting your neighbor have a pool because you hear splashing and actually seeing the diving board over the fence.
Precisely. And Bruzon put it well. This discovery contributes to a deeper understanding of the processes that have shaped Venus's evolution. It's a piece of the puzzle of how Venus ended up the way it is, why it took such a different path from Earth.
So we found the skylight, we know the tube is huge, we know how it formed, what happens next? Because we can't just send a spelunker down there with a rope and a headlamp.
Not unless that spelunker is made of titanium and doesn't mind 900-degree Fahrenheit heat.
Fair point, but this discovery feels like a targeting beacon.
It is. It is basically a giant neon sign saying, look here. And the timing is perfect because we're entering a new golden age of Venus exploration.
We have some missions on the books, don't we? It feels like Venus is finally getting some attention again.
We do. For a long time, Venus was the neglected sibling. Everyone wanted to go to Mars. But that is changing. We have major missions coming up in the early 2030s. ESA's Envision and NASA's Veritas.
And a discovery like this just makes those missions even more exciting.
Much more. It gives them a prime target. These missions represent a massive technological leap over Magellan. Remember, Magellan was late 80s, early 90s tech.
Floppy disks and dial-up modems.
It did an amazing job, but it was like using a fax machine compared to a modern smartphone.
So what can the new guys do that Magellan couldn't?
Resolution is the first big jump. Magellan's resolution was roughly 100 to 200 meters per pixel, so a feature had to be about the size of a football stadium to really show up clearly.
Okay.
Veritas and Envision will be getting down to 15 to 30 meters per pixel in some modes.
So instead of a blurry pixel that might be a hole, we get high def.
We get much clearer images. We will be able to study small surface pits, fractures, and textures in much greater detail. We can see the exact shape of the skylight's rim. But Envision, the European mission, has a secret weapon that is particularly relevant to this story.
Oh, what is it packing?
It's carrying an instrument called a subsurface radar sounder.
That sounds like something from Star Trek. Commander, activate the subsurface sounder.
It acts like a ground-penetrating radar. Unlike Magellan, which just bounced waves off the surface skin, the subsurface radar sounder operates at a lower frequency that can probe into the planet.
Wait, so it can see through the rock?
To a degree, yes. It looks for dielectric boundaries, changes in material properties beneath the surface, so it can see the boundary between solid rock and an empty void. It can see down to depths of several hundred meters.
That's a game changer.
It is. Think about it. Right now, we only found this one tube because the roof collapsed. We found the accident. We found the skylight.
It's a broken tube.
Exactly. But there could be hundreds, maybe thousands, of intact tubes, pristine, sealed environments that we have no idea about because the surface looks flat and unbroken.
And Envision could find them.
Envision could fly over a flat plane and detect the hollow void underneath. It could map the entire underground network without ever needing a skylight.
It's like X-ray vision for the planet.
Essentially. Bruzone calls this discovery only the beginning of a long and fascinating research activity. And he's right. We are transitioning from looking at the map to reading the history written inside the rock.
It really makes you appreciate how science works. It's this baton pass. Magellan runs the first leg in the 90s, collects the data, passes it to the researchers in 2026 who analyze it with new tools, and they pass the baton to Envision and Veritas to go back and look closer with even better tools.
And each step clarifies the picture. We go from, is there volcanism, to here is a lava tube, to let's map the entire underground plumbing of Venus.
I want to circle back to something we touched on earlier, the so what for the average person. Because let's be honest, we aren't planning a vacation to Venus anytime soon.
Probably not.
The travel brochures would be terrifying. Come for the acid rain, stay for the crushing pressure.
It's not a top destination, no.
But why does finding a cave on Venus matter to us here on Earth, aside from just being undeniably cool?
Well, beyond the pure joy of discovery, which shouldn't be underestimated,
Of course.
understanding Venus is crucial for understanding Earth.
Yeah.
Have to remember the twin narrative.
Right. Same size, same mass, basically.
Formed in the same part of the solar system out of the same cloud of dust and gas.
Right.
Yet one is a paradise where we can record podcasts and drink coffee, and the other is a runaway greenhouse oven.
So what went wrong?
That's the question. Understanding the volcanic history of Venus, how it outgassed, how the heat escaped from its interior or didn't escape, helps us understand planetary evolution. It helps us model our own planet's climate and future.
It's a cautionary tale.
In a way. But also, studying these extreme environments tests our physics. If our geological models work on Earth, and they work on the Moon, and they work on Venus, then we can be much more confident that we really understand the universe.
And if they don't?
If they break when we apply them to Venus, then we're missing something fundamental. Venus is the ultimate stress test for our science. Its extremes push our theories to their limits.
That's a great point. If you can predict a lava tube on a planet you can't even see and then find it, you know your math is solid.
Exactly. And there is a practical angle for space exploration, too. If we ever do send long-term probes or even humans to other worlds, like the Moon or Mars lava tubes, are the prime real estate.
Because they are shielded.
Yes, space is dangerous. The surface of the Moon or Mars is constantly bombarded with cosmic rays and solar radiation.
Which is bad for astronauts and electronics.
It's lethal over the long term. And you have micrometeoroids, which are like tiny bullets. And the temperature swings can be hundreds of degrees between day and night.
But inside the tube,
you have a roof, a very thick roof of solid rock. It blocks the radiation almost completely. It stabilizes the temperature. It protects you from impacts. They are natural habitats just waiting for us.
So in a way, hunting for caves on Venus helps us hunt for bases on Mars.
It is all connected. It refines our ability to find them everywhere. It teaches us what to look for in radar data, what the telltale signs are. Comparative planetology lifts all boats.
I love that. Okay, let's do a quick recap of what we've learned today before we get to the final thought. We started with a 30-year-old map from a dead spacecraft.
A Magellan mission. A ghost ship.
Researchers at the University of Trento took that data, applied some 2026 magic new algorithms and analysis techniques, and looked at a volcanic region called Nyx Mons.
The Mountain of Night.
Yeah.
And there they identified a skylight, a collapsed pit in a volcanic range.
Which turned out to be the front door to a monster. A lava tube 1 kilometer wide, buried under 150 meters of rock, extending for at least 45 kilometers.
A structure shaped by Venus's unique conditions. Lowish gravity, and a crushing hot atmosphere, creating an insulated superhighway for lava.
And finally, we learn that this is just the prequel. The real movie starts when Envision and Veritas get there with their ground-penetrating radar to map the rest of the network.
A perfect summary.
It really makes you think about what else is hiding in that data. If Magellan has been holding on to this secret for 30 years, what other pixels are just waiting for someone to invent the right algorithm?
That is the beauty of archival data. It never expires. It just waits for the right question to be asked, or for the right tools to be invented.
Before we wrap up, I want to leave you with a thought. We talked about the conditions on the surface of Venus. Hellish, unsurvivable, acid, heat, pressure.
Yes, the worst place imaginable, as you said.
But then we talked about this tube.
The pyroduct.
150 meters of rock is a lot of shielding. It blocks the cosmic radiation. It thermally insulates from the surface swings, if there are any. We know the pressure inside would still be immense. It's an open system connected to the atmosphere. But inside that tube, cut off from the acid clouds and the surface winds, it's a different world.
It is a stable environment.
Yeah.
Dark, certainly. Hot, absolutely.
Yeah.
But stable, protected.
If a 1 kilometer wide tunnel exists under Nyx Mons, what is in it? Is it just empty space, just black, pristine basalt frozen in time? Or is it, as we hinted at, the most interesting real estate on the planet?
That is the billion-dollar question. On Earth, caves are often biological hotspots. They protect unique forms of life. On Mars, we hope they might preserve signs of ancient life from a time when the surface was more habitable.
Right.
On Venus?
Yeah, on Venus. What could possibly survive there?
Well, probably nothing as we know it. But it is the only place on the entire planet where the surface chaos doesn't reach. If there was ever anything on Venus that wanted to hide, that wanted to survive the transition to the hellscape we see today, that is where it would go.
A kingdom in the dark.
Waiting for a radar that can see in the dark.
I love it. We will be watching closely as Envision and Veritas get ready to launch. Until then, keep looking up. And maybe keep looking down.
Beneath the surface.
Thanks for listening to this deep dive.
A pleasure as always.